Okay, let's start again. We have two more talks in this morning session, still focused on laser diagnostics, on laser sensing, I guess. And the next speaker is Professor Aamir Farooq, who has been here at KAUST for longer than I can remember. He doesn't even write it anymore on his bio. So I think many of you already know him. And if you don't, you see his lab and the amazing research he's been doing these years. Today is going to talk a little bit more focused on laser-based sensing. And the floor is all yours.
Okay. All right. Thank you, Gaetano. Everyone is here. Call everyone who's still outside. They don't want to miss this one. Okay. So I'm going to talk about some sensing work that we've been doing recently and a little bit on property prediction. So first of all, I want to thank my student, Mohammed C. He made most of the slides. So if you don't like them, then you talk to him. Okay, so we have talked about this picture of aviation, synthetic or alternative fuels a few times already in this meeting. So you start with some sort of source of hydrogen, hopefully some green source. You need some CO2, either captured from plants or maybe direct air capture. And in that case, actually, you can argue that it becomes carbon negative. Then you need some sort of a chemical plant around there. It's kind of like our refineries these days. And then you convert these to the fuels that you need, whether it's gasoline, jet fuel, diesel, and all that. So it all looks good, but as we have heard from other speakers as well, on each part of this step, there are a lot of challenges, a lot of things that still need to happen for this process or this entire picture to be optimized and start producing volumes and start becoming competitive. I think that's the key problem right now, is that these processes exist, but they are not competitive with what we have from conventional fuels. But nevertheless, this will become more prevalent as we go on. Specifically for aviation fuels, this is a picture which shows the variation in the composition of conventional jet fuels and the synthetic. And for synthetic, these are the ones which are included in this picture and taken from this paper. So alcohol to jet, Fischer-Tropsch, HEFA, and these other processes. The ones in blue are the conventional fuel compositions, and the green are the synthetic fuels. So what this picture basically shows is that there's a lot more variation in the composition of the fuels that you get from the synthetic routes, which has challenges, but as we learned already, has opportunities also for producing maybe the most optimal fuel that you can have. So in that context, what we focus on in my group is trying to sense these different formulations of fuels and also try to predict the properties of these different combinations or compositions of fuels. So sensing in aviation and aerospace has many use cases. We just learned one from Eddie on detecting combustion or detecting flame fronts or whatnot. You can have sensors for looking at leaks, maybe VOC or other toxic emissions. You can also think of having an onboard fuel quality sensor. So that could become quite useful when you have a lot of variation in the fuels. And then if you want to, although there are not that many knobs in jet engines, but still if you want to take some action or at least know how from airport 1 to airport 2, or when you fill, what has changed in the fuel as the fuel mix evolves, such kind of sensors can be quite useful. And then beyond in the upper planets and all that, there's also a lot of applications of sensing and spectroscopy. For example, if you look at this image from the James Webb Space Telescope, there's the spectra of different molecules that have been detected from different planets and all that. So spectroscopy and sensing plays a very important role in that domain as well. So in my group here at KAUST and at other places, we've been working on what we call a universal spectroscopy platform. Basically, a collection of methods, systems, and databases to develop sensors for a variety of applications, from environmental monitoring to maybe for this talk, the second column for in the energy and transportation. There are also applications in the health sector that we have done in the past and are now getting back to for health monitoring, security and safety applications, and a number of other industries. Okay, so with that introduction, this is the outline of my talk. You basically see that there's a lot of dealing sort of things there. Basically, what I'm going to really focus on today is the application or use of machine learning-based methods for dealing with different challenges that we face in sensing methods. And then towards the end, I'll talk, if time allows, a bit on the prediction of fuel properties. So all of what I'll show today is based on a relatively simple technique of absorption spectroscopy. So you start with a semiconductor laser, send it through your medium of interest, which could be your jet fuel, could be your combustor, could be your jet engine or whatnot, where a lot is happening. And then you look at the change in the intensity of the laser from I0 to IT. And this change in intensity is related through this, again, relatively simple relationship, Beer-Lambert law, where what you measure, the logarithm of the ratio of these two intensities depends on the absorption cross-section of the molecules that you have there, their number density, the path length. So this is a path averaged measurement. It gives you an average measurement over the propagation length, and then the mole fraction of the species, which is typically for the work that we do is of interest here, the mole fraction of one species in a sea of other species. But the technique can also be used to measure temperature, pressure, density, mass flux, or whatnot. What I really want to highlight here is that the components that we use here are really tiny, really small. So you see with respect to a coin there, the laser is pretty small, semiconductor laser, the photodetector is small. So this is something that this kind of methods are really ready or are really, they have great potential for field applications and for adaptation as portable devices because of their small size. So this field of absorption spectroscopy, sometimes also called TDLAS and other names, has been really well developed over the years for single species detection. So you can find sensors in the market, even commercial sensors, as well as in research, which are developed using this method to detect a single species like carbon monoxide, water, or whatnot. Where it becomes more challenging with this technique is to do multi-speciation, to detect multiple species simultaneously. And in principle, it's again very simple. When there are multiple species absorbing, they just linearly add up, especially if it's in the gas phase. And the liquid phase, there are some other effects that we have to study, and we've done some work on that, which I'll not talk about that today. But again, the challenge that I've talked about today is how to do multi-speciation with this simple technique. So the first case is the first dealing, or the first thing we do is that dealing with non-interference. So it's in the order of problems that I'll show, it's a relatively simpler problem, but not that simple as well. So again, the use case where we applied this was the detection of this family of aromatics called BTEX, benzene, toluene, ethylbenzene, and 3 isomers of xylenes. They have a lot of applications, a lot of importance in the petrochemical industry, but also they are VOCs, so they are also toxic. So what you basically see is that the backbone of all of these 6 molecules is the aromatic structure, okay? And then there are some branching which differ. So because of that, if we look at the spectra of these molecules, and so throughout this talk, you'll see a lot of plots like this. So just to make it clear, typically there's wavelength or wave numbers on the x-axis. So wave number is just the inverse of wavelength, and then you will have absorbance on the y-axis. So what you see is that in this particular wavelength region, which we call the CH stretch region, the spectra overlap quite a bit. But we are looking at a relatively longer region of about 100 wave numbers. What are typical lasers that I showed you on the last slide with a coin, a typical laser can only access a couple of wave numbers. So I zoomed into this region, and then you basically see that there's a lot of overlap of these there was overlap already, but now it's much more flatter. And so what your sensor or what I showed previously would measure would be sum of all of this, right? But what you want is how to decompose that. You want each species to be determined and measured quantitatively. So that's where the challenge comes, multi-speciation in a very narrow range of wavelengths. So we can do some normalization of this previous picture, and we start seeing some structure there, but it's still, there's quite a bit of overlap. So long story short, this work was done a couple of years ago. We looked at a number of machine learning models. Because you cannot do a lot of experiments, so we relied a lot on simulated data. So about 5,000 simulated spectra, some measured spectra, combined them and built and trained a neural network-based machine learning model, and then validated that with some new data which was not part of the training process. And in summary, we compared some methods. For example, the very simple one is the multilinear regression. And what you see here is on y-axis is the predicted. I don't know what's that for, so that's C's fault. On x-axis is manometric measurement. So the ideal would be everything along the diagonal. So this multilinear regression is not able to separate out the signals of these molecules. Sport vector machine does slightly better. XGBoost even better, and then we get the best performance with deep neural networks, where you are able to separate out the signals from a mixture of these BTECs, and you can then selectively determine their quantities. So now we are in the process of converting this lab scale prototype to, again, going up the TRL scale to a prototype that can, for example, be mounted on a drone or put on a vehicle and moved around petrochemical facilities for detection of these BTEX molecules. We've published a few papers on that. After the first one, we looked at the path length enhancement, how to determine from parts per million to parts per billion levels of this. So this axis was parts per million, but you can do some cavity-based technique to take it down to parts per billion levels. We also applied this method to high temperatures, so some sort of combustion application, and then very recently did an application of this method for chemically reacting environment. What you saw before was all what I showed here, and previous work was environmental monitoring. Okay, so that's one. The second case now, the first one, you knew the interfering species, and there was overlap that we had to deal with. But in real life, you can have situations where you don't know the interfering species, so that's what we call unknown interference. So the method that we use here is called augmentations. So just to schematically show this, with your laser, you would like to detect the blue molecules, but avoid the interference from the red ones, okay? So you would want your laser to go in this zigzag fashion, but obviously laser doesn't go like that. It goes in a straight line, so it will have a signal from both blue and red. So you know the reference spectra of blue, but you don't know anything about the red ones. They're just interfering species, and in real life, this can be the case. So just to set up the problem, so this is a numerical problem only. We are now looking at its experimental demonstration. So we want to detect these 10 species. Again, benzene, ethylene, some common VOCs that you want to detect, and this is their spectra. And so we know this. And there's overlap, but we already looked at that we can deal with that overlap. But the challenge here is that you can have interference from another set of 10 species, for example, which you know nothing about, right? So this is really unknown at the time of the training of the problem. Okay, so just to explain that further, we use a lot of synthetic data, 600,000 synthetic data of the random mixtures of our target species in the training phase. But then when we test, then we'll have to assume, or we'll have to basically use the interfering species spectra, which was not known to us at the training phase. So the way we do that is this method called, well known in signal processing and mostly in image world, called augmentations. So you take what is known to you, what I call original here. So in the previous example, what is known is only the left side of this, okay, the left spectra, and then you do different mathematical operation to it. So you flip it, you mirror it, and then you dilate it, kind of stretch it, and a combination of that. And these fictitious spectra is what we use in the model and tell it, the interfering species may look something like this, okay? They will not be exactly like this, but this turns out that this is sufficient or at least gives much improved performance. So again, in the training of this problem, we give them the spectra of what we want to target, but in the testing, we add the known spectra there, but the main point there is this fictitious spectra from mirroring, dilating, and all that is what we add. And then this is sent to a pretty standard kind of CNN model to then determine the mole fractions of the species of interest. So just to summarize the results, there's a lot going on here. What we have on y-axis is a mean absolute error of the detection of these target species. On x-axis are different methods. The best would be if you know everything. So known, like if you know your interfering species, of course, then your mean absolute error is the lowest. None would mean that you know nothing about your interfering species, so the errors are quite high. And then as we apply some of these augmentation methods that I mentioned, flip, mirror, dilate, all of them, and some fine tuning, then our errors drop down and they come to, of course, they'll never come to the known, the ideal scenario, but they come pretty close to that level. So this method then helps us deal with this unknown interfering species. Okay, so the next sort of example that I show in, again, dealing with these multi-speciation, because each problem has its own challenges. In this case, we are dealing with some species which have either flat features. Kind of we saw that with the first BTEX example, but maybe another compounding problem that can come, which we didn't say, is that one of the species has very low absorbance. Okay, so now we have these two challenges combined. We are trying to detect one species maybe in parts per billion level, and others are in percentage level, right? So, and they are overlapping, okay, and they could be flat. So we use something called spectral feature engineering. It's again, in concept, it's not a very complicated thing, but the results are very encouraging. So just as a case study, first I'll show a simulation-based case study, and then an experimental one as well. So again, we want to detect these four aromatics, but what you see is that one of them is very high. This one is quite low in comparison, and then they are flat. So we do a very simple operation. We take the first derivative of these spectra, and then we do a convolution of the first derivative with the reference spectra, and then we get the picture on the far right. So it's a convolution of the two, the reference and the first derivative, and then we find that this simple sort of operation actually really improves the performance of the machine learning model in trying to selectively determine the amounts of these species. So again, you have a standard model, which wouldn't do that sort of spectral engineering, feature engineering, and then you have the feature engineering model. And what you see on the right is what is commonly used for these machine learning models is the loss function. And the loss function for the case of the standard model, it sort of plateaus, the yellow one, after about 5 epochs, whereas the one for the feature engineering model continues to drop, which shows that the model keeps improving as you run through different iterations. Okay, so just to show again the comparison, the standard model, we used about 1,000 mixture spectra, and you see that again this should be in the best case should be along the diagonal, the predicted and the true values, and we see that it's okay, but there's quite a bit of scatter still with the R-square values around 0.9 with the standard model. But then once we apply the feature engineering, which was again take the derivative, do the convolution, then we see a much improved performance of the model in trying to separate out these species and measure output their quantities. So then we applied this method outside of the numerics, and in the experimental validation also, we chose a different problem here. So we wanted to determine ethylene concentration in the presence of a few other species. So this is our problem. So we have methane, ethane, propane, propyne being high in concentrations, and then here at the very bottom, this line here is ethylene. Okay. So as I said earlier, that the new challenge here also is that what you're trying to detect has very low absorbance compared to others, and it has a flat feature. Okay, so ethylene is really low here. So again, we take the first derivative, and we take the convolution with the reference spectra. And then there's a very well-known process in sensing, something called Allen deviation. So we do that to make sure that the very low absorbance of ethylene is still detectable by our detection system, which in this case was if we average over about 8 seconds. So from this experimental, so we collected 47 actual experimental data of these C1 to C3 molecules that I showed on the last slide. Again, on those collected experimental spectra, if we apply the standard model without any feature engineering, then the labels are missing there. But for 4 of the 5 species, you still get a diagonal result, good result. But for the one which is looking flat is ethylene. So ethylene, because of its low absorbance and flat feature, the model is not able to predict it accurately. But then once we apply this convolution or feature engineering, you see that the ethylene line also turns diagonal, indicating that now we have a very good determination of ethylene as well, albeit it's very, very low concentration and very flat spectral feature. Okay, so the last example that I'll give is called unsupervised source separation, or sometimes also called blind source separation. This is used for, again, another case scenario where you don't know the reference spectra of the species that you want to detect, but also you want to determine that, because this could have many applications. For example, room temperature databases are available. So you can have spectral databases at room temperature, but if you want to develop a database at high temperatures, you don't have that. And to do that species by species would take a really huge effort, but this sort of method can be used to make one or multiple high temperature mixture measurements and then dissolve them into the reference spectra. So this problem actually is a very old problem and comes from audio signals. So imagine that now all of us start talking at the same time, right? Then a microphone or whatnot will collect all of the voices at the same time, right? And you can't really then, at least as a listener that I'm here, and this is actually, I don't know, maybe some of you have heard of it, it's called a cocktail party problem. So if you're on a, well-known, in a cocktail party, everyone is speaking at the same time, then one of us, maybe you try to listen to one person, right? What is he saying or she saying, right? Actually, our brain is very smart. Our brain can actually lock into one voice, right? So it can do this blind source separation, but for one particular voice. But in signal processing, this is much more challenging. So anyways, the point is that if you have all of these voices coming in at the same time, you need some sort of a method to then able to separate, to say, Gaetano was saying this, Aamir was saying this, Diana was saying this. So to be able to separate it out is what the problem is. And as I said, it has a long history. It started in 1950s. In 1970s and 90s, the two methods which became really popular for this were the principal component analysis. Many of you know about that, and independent component analysis, and had some success in solving this problem. More recently, a method that became quite popular is called NMF, non-negative matrix factorization. But then very recently, the method which has become popular is, of course, based on deep learning and AI to tackle this problem. So communities of image community and the audio community are already applying deep learning AI methods for this problem. And even if you read the Wikipedia article on this, it tells you that this is still a problem in progress. So there's still, because why is that? That this is inherently, forgot to say, this is inherently an underdetermined problem, right? So it's, you can't really say that from all of these voices that you'll be able to actually perfectly separate out. It is an underdetermined problem. So any solution you have actually tries to approximate to the original problem. So in that context, there's still a lot of progress happening. So how do we apply it from audio to spectroscopy? So there are a lot of parallels. Again, in the audio community, they have mixed audio signals. In my spectroscopy problem, we have mixed absorbance spectra. Okay, The outputs are also somewhat similar. In the audio case, you want to know the number of independent sources, how many people were speaking at the same time, and what was each person saying, basically, right? Same on the for my spectroscopy problem. I want to know how many species were there from a mixture, species absorbing at the same time. I also want to get the independent spectra of each species, okay, and the concentration of each species, okay. And the only input, as you see, is the mixed absorbance spectra, or again in this case, the mixed audio signal of all of us speaking at the same time. So the method that we use here is an autoencoder problem. So basically, you have an encoder which encodes the mixture spectra onto a latent space Z. Okay, and then you have a learnable function f of z from that latent space, where then the decoder will reconstruct the input spectrum, and then by using this back propagation error between the output and the input, it'll try to then build the reference spectra as well as output the concentrations of the species. So here's an example of that in an animation that initially when you feed a mixture spectra to it, maybe it runs one more time, then basically there's a lot of noise in the beginning. So, but then through a number of epochs and running through it again, then it converges to a solution, which in this case we compare it to something which was known, which is just to build up the problem, and then it comes out to be pretty close to that. So over these epochs or iterations, then it learns that. So we applied this to a case study of two species. So that would be two species absorbing at the same time, or two people speaking at the same time. Okay. So this would be the input spectra, and the reconstructed spectra is pretty close to that, with a relative error of less than 0.2%. A little bit high error on this side because of the low values there. Then we applied it to, so it becomes harder and harder, the problem. Again, you understand this, right? The more people are speaking or the more species are there. So applied it to a case of 4 species. Again, we get a pretty good performance in terms of what we are predicting on the top, and what could have been known, right? It's in a real problem, it's not known, but just in the development phase, what could have been known. So there's a pretty good comparison there. But then we start seeing a little bit of like problems there. In the reconstruction. But nevertheless, what we would be interested in is the concentrations of these 4 species, and the actual and predicted are still lie along the diagonal. Now we make it even harder. We go to a case of 8 species. Okay, so this would be, for example, the concentrations of them, or what you would eventually determine from the method. So input spectra, this is a mixture spectra, 8 species absorbing at the same time. Again, the model is able to recover that through the back propagation scheme. In this case, what you see is that now the error is higher. From 0.2% for 2 species, it's about 3 to 4% for the case of 8 species. So the problem becomes harder and harder as you have more and more number of species. And even in terms of, for these 8 species problem, in terms of recovering the spectra, you start seeing some noise and some issues there, because again there's just a lot more going on there, but it still does an acceptable performance in terms of the predicting the species concentration along the diagonal. Okay, so with that, I'll just take a quick tangent, and in the interest of time, I won't talk much about this part of the talk, but this is the prediction of fuel properties from IR spectra. As I mentioned in the beginning, the landscape or the composition of these alternative fuels or synthetic fuels is different from conventional fuels, and there can be a lot more variation there. Okay? So the way and what you can do, of course, is that you are interested in a number of properties like density, viscosity, flash point, energy content, or whatnot, right? So there are obviously tests in the lab for all of those, but those tests can be time consuming, and they can take quite a bit of the fuel to do this. And sometimes through these processes, you make very little quantity. So the method that we use and develop for property prediction of these new fuels is based on the IR spectra, because the IR spectra contains information about the molecular fingerprints, about the bonds. So whether it's the CH bond, CO bond, OH stretching, or OH bonds and whatnot. So that information that of the molecular structure or molecular fingerprint is encoded onto the IR spectrum. So we make measurements of the IR spectrum and use that to predict fuel properties. So over the last couple of years, we did this work for gasoline and diesel-like fuels initially. So to predict the properties, for example, RON, MON, C by H ratio, density, and all that. So we predicted those properties. So input is spectra, and the output are these properties. So next, what we are working on these days is applying this method to aviation fuel property prediction. Again, the framework is pretty similar. You have as the input the spectra, IR spectra, that you either measure through an FTIR or you measure through a laser, depends on how much of a wavelength region you want to cover, and that has some intricacies there as well. So you take this spectra, send it to some sort of machine learning based model that you have to optimize for that problem, and then use that to predict the properties of interest. As I said earlier, density, viscosity at different temperatures, heat of combustion, flash point, freezing point, etc. So we have some results on that, but in the interest of time, I'll skip that and just finish up. Am I on time? Okay. So in summary, what I've shown you today is that machine learning really enhances. It's basically a signal processing sort of a method, but it enables you to do more complicated problems than what you would do with this, at least the simple sensor architecture that we try to use of absorption spectroscopy. So I showed a few examples of dealing with initially known interference, then unknown interference through augmentation, using feature engineering, using derivatives and I'm overly excited. The derivatives and convolution of those, and then the really interesting problem of the blind source separation. So that's we applied it for spectroscopy, and then finally, sort of work in progress is the aviation fuel property prediction using spectra. So before I end, I would like to thank again Mohammed C for helping me prepare the presentation. And this work was contributed by two of my former students, very recently graduated. Imad is now a postdoc at MIT, and Mhanna is a postdoc at University of British Columbia. So both of them were my machine learning gurus, and then Mohammed C has taken that over, and then the entire FASTA group. Actually, it's a good time to propagate my new branding of the group, right? I don't know what you guys think of it, but we rebranded our research group. We call it the FASTA group, Farooq's group for advanced sensing technology and energy transfer, right? So we try to do everything fast, but faster than others. Okay,
great. Time for questions.
Thanks, Aamir. Excellent. You showed some really interesting comparison between different strategies or analysis of your data for absorption when for known species. Do you think you will obtain the same result, same evaluation of the strategies if you are looking at emission spectra instead of absorption spectra?
Yes, absolutely. Okay. I think the same methods can be applied to emission spectra. Absolutely, yes. Short answer, but yes, yeah.
Thanks, Aamir. Very interesting. For the SAFs, they usually have less amount of aromatics, and that's why they are more clean. Do you think this will make this technology or strategy even better for SAF fuels or SAF-like fuels, or it wouldn't really change much of it?
I think the strategies apply equally to whether there are aromatics or not. It's just so happened that maybe two of my examples were on aromatics, but if you don't have aromatics, then you primarily in SAFs, you will have a lot of paraffins, maybe a lot of linear paraffins. And in that case as well, there's a lot of overlap of their spectra, especially in what we call the CH stretch region. So the strategy would also apply equally well to a bunch of paraffins that you want to detect and isolate their contributions. So yeah, it would work equally well.
Thank you.
I used to ask him questions in my class, so it's his time. His time to take it back. Yes.
Yes, indeed. Thank you for a great presentation. I just have a quick question. So I also noticed that some models use results of GC analysis in order to predict a lot of field-relevant properties. How do you compare the two approaches, being FTIR and then the other composition, which you get from gas chromatography or something similar?
Yeah. So gas chromatography, some people call it the gold standard of measuring gaseous species. I think it's really well developed over the years, and it's really great. But as any of you who have used GC, you know it's a big bulky instrument, right? You need some sort of calibration. There's you have your different cycles in there. You have retention times and all that. So it does really good. But what we are trying to develop here is field deployable portable instruments, right? So which and I didn't show it today, but our initial work that we did for a sponsor, they actually we showed them some results, and they were like, no, we wouldn't believe it until you compare with a GC, right? So then we had to compare with a GC, and we actually got comparable results, but in some cases actually better. We were able to detect much smaller quantities with our sensor. But the other big advantage is the time response, right? So we can do these measurements on a sub-second, even if we really needed millisecond levels, and the GCs take some time to do that.
There are no more questions. Let's thank Aamir again.